So next, let's consider the same beam, but we change the joint C to rocker instead of a fixed wall. So in this case, member joint C has only one member because there's BC, and compared to joint B, you have BC and BA. Compared to joint A, you have BA and wall. But joint C, you have nothing on the right hand side. So your distribution factor will be different compared to the previous. This is K over summation of K, because they only have one K. So is divided by the same K value. So your distribution factor is 1 compared to previous one. Your because it is wall, so your distribution factor is 0. As you can see here, distribution factor at joint C is 0. So that is now established. So the other FEMs and distribution factor remains the same. So you have this table here on line 1. So you can see your DF is similar except for joint C. So we solve for FEM is also the same, 8,000 and negative 8,000, same as the previous. So first things first is to lock and unlock lah. When you unlock your moment here, 8,000 become negative 8,000. Then you carry because the distribution factor is 1, so you being distributed wholly to negative 8,000. And then you distribute to joint B, half of it. As you can see here, half is 4,000. So carry over to B. So then you can see that this here is already balanced. 8,000 and negative 8,000 is balanced. So now we move on to joint B. As you can see here, we have negative 8,000 and negative 4,000. So to sum it up, we get 12,000. Unlock it, apply opposite moment. So you have 12,000. 12,000 distribute to BA and BC by this distribution factor. You get this 4,800 and 7,200. As you can see here, 0.4 times 12,000, get this value, and 0.6 times 12,000, you get 7,200 on line 4. So this moment at joint B need to be distributed over to joint A and joint C respectively. So half of it, half of 4,800 will be 2,400, and half of 7,200, 3,600. So so this is balanced now because being distributed to adjacent joint. So as you can see, there's a 3,600 moment at joint C right now. It is not balanced. So you need to do the same. Unlock and unlock. So 3,600 unlock become negative 3,600, and then distribute wholly 1 times by 1. So you get this value, negative 3,600. And then this moment need to be carry over to joint B half of it. So you get 1,000, negative 1,800. So now we move on to joint B. We have negative 1,800. Unlock is 1,800, right? So you once you have applied the opposite moment, then distribute to BA and BC, 0.4 and 0.6, which is 720 and 1080 here. And then carry over. So this is a repetition. As you can see, 4 is similar to 6, similar to 8. This is a repetition which we are solving, distributing the moment from joint to joints. So each of the steps from lines 3 to 14 should be thoroughly understood. You need to understand all of it because it is a repetition. So then summing up the moments, the final results are shown on line 15, where it is seen that the final moments now satisfy joint equilibrium. As you can see here, joint B is balanced 5, 6, 4, 7, which is similar to joint in member BC, and joint C is 0 moment because it is spin. So you need to repeat this up until your value of moment being distributed is small enough that you get a balanced moment at joint. So that is a bit tedious and long, and you go from join to join, C, B, and then C back. You are lucky because we are lucky because the join A doesn't distribute any moments. Another method is to apply the moment concurrently. Instead of we go from C to B and then back to C because there is no moment A. We can do it concurrently. We apply moment. As you can see here, this is the FEM that we have calculated from the formula, and then we unlock the moment. This is the in between this there is a phase of unlocking the moment where 8,000 become negative 8,000, and then this negative 8,000 become 8,000, and then the unlock moment times the distribution factor, you get this value lah, the distribute the row here, the IST row at line 3 ni. So negative 8,000 times 1, so you get negative 8,000, but this one is 8,000 times 0.6, you get 4,800. 8,000 times 0.4, you get 3,600. So this is the distributed moment. So we do it concurrently, B and C, because we have moment at B and C, member BC lah. So this moment, distributed moment carried over to the adjacent joints. So 4,000 member BC. So you need to carry over the moment from B to C lah. So 4,800 divided by half, 2,400, and then this negative 8,000 divided by half, you get negative 4,000. Similar to this BA moment at member BA distributed 1,600. So we can do another example here. So we have moment being carried over at line 4. So unlock. The first one is unlock the moment. So apply like opposite, like apply negative. Apply negative here. So you get negative 8,400. Then you apply negative and then you times the distribution factor. So in this case times 1. So you get this negative 2,400. And this one is negative 4,000, unlock 4,000 times distribution factor, so you get this row lah, 24 and 1,600 here. Then carry over to 800. So as similar to before, as you can see at column A, you don't have any distribution because the distribution factor is 0. So there is no moment here being carried over. There is no moment at A being carried over to join B, which reduce the steps. So as you can see here, back to the moment here, then you carry over to 800, 1,200, and 1,200 here, and then this value of moment at this line 6 or line CO here, so you need to unlock, so it becomes negative 1,200, and then times distribution factor becomes negative 1,200. So this one negative 1,200, positive, apply negative, so you get positive 1,200, and then times distribution factor, you get this 720 and 480. Then you need to carry over to 40, 360, and then this negative 600. As you go along the way up until the line 21 here, you can see the number is slowly reducing. They call it convergence. So it slowly converge up until line 23. You can say it's small enough, 0.24, 0.37, and negative 0.61. So small enough so that you can have this balance moment when you sum up all the column here, all the row here towards this. So you get a balance moment. So that is our main objective in doing moment distribution. So by comparison, this method gives a slower convergence to the answer compared to the previous method. However, it is more easy to apply this moment because you can do it concurrently. So finally, using the results here at line 24, you can draw the free body diagram. You can resolve for shear. You can calculate the shear for each member. As you can see at 12.6D, at the top is AB member AB, and the bottom is member BC. You have this moment. This moment here is similar to this. So you have a moment at A is 2823, and then moment at B is 5647. Important to highlight the denotation of negative positive. As you can see, positive is taken as clockwise, clockwise moment. And negative is taken as counterclockwise moment. As you can see here, moment at member BC is negative 5647 here. So because it is a negative moment. So based on this moment, you can solve for shear. Take moment at B. So you can solve for VA. Take moment, and then you sum VA, sum of the FY. So you get VB. The same goes to this member BC. You get VB on the right hand side and VC. As you can see here, the shear at joint B, we have value on the left hand side and right hand side. As you can see here, is 564.7 pounds on the left hand side. But on the right hand side, you have 2682.4 of shear force. So that is a thing to highlight and not take it lightly when you calculate for shear. To conclude, this method follows the fundamental of any displacement method as we done before, force method. So there's a process to establish the relationship between load displacement and at each joint, and then to satisfy to establish the relationship between load and displacement, how much load being applied and how much displacement should be experienced by the member. But then again, in this method, we satisfy the rotation compatibility by using a moment balance process. We try to balance out the moments, distribute the moment in the process, so it is a bit easier and doesn't rely on the we don't need to use an equation of displacement or anything. So next we're gonna sum up on all the procedure on this method, just on the fundamentals, so we can go through that, and also we go through some more examples for you to do yourself or to get deeper understanding.